Now, we can look at the details of all these different types of blood spatter and get some more information about the circumstances at a crime scene. Okay, there are a few things that can provide us clues as to what happened at the crime scene. The first thing that can provide us these clues is the shape of the individual blood drop, or the shape of that blood spatter. First and foremost, this shape can give us a clue as to the direction from which the blood spatter originated. So it'll tell us the direction of, say, travel of that particular blood drop. So if you look at this first blood stain here, and we've got our normal 90-degree angle just dropped directly onto a smooth surface. You can tell that because it's got a smooth margin. But if you have a longer shaped drop and it's got a tail, that tail is going to point in the direction of travel, or the direction that that blood was traveling when it hit that particular surface. So here again, it's another picture. We've got our main blood drop here, and we've got the tail, and that tail points in the direction of travel. So the blood spatter, the blood drop, came from down this direction, hit here, and was going that way. Okay, so we can look at this as well. We can see we've got a bunch of blood drops here that are 90 degrees. We've got these lines of blood drops or blood spatter. All the tails are pointing over here to the right. That means that the blood was traveling to the right. So that tail tells us which direction this was traveling in. Also, there's a mathematical relationship between the width and the length of an elliptical blood stain. This is really nice because this will allow us for the calculation, or allow us to calculate an angle of impact, or AOI. Okay, so an angle of impact. So this tells us what angle this blood drop hit a surface at, be it the floor, the wall, or the ceiling, or whatever else. So a circular blood stain, or a circular drop, this is when the width is going to equal the length. So you've got the same width and the same length of the blood drop right across those fattest parts. So this tells you that the blood fell straight down and it hit the surface at a 90-degree angle. An elongated drop, however, this is where the width is less than the length. So the width is much smaller than the length. So let's look at these. So you want to measure the width at this fattest part. So here's the width, and look how long that length is. So either you're going to have the width being equal to the length, or the width being less than the length. Always, always, always think about that. So anytime the width is less than the length, this indicates momentum. So this will tell us that at direction that the blood drop was moving along, and that momentum is going to keep the blood moving in the direction it was traveling. So as the droplet moves away from its source, let's say it's hitting a wall at a 50-degree angle. Why not? Okay, so it's hitting the wall at a 50-degree angle. It's going to continue moving along that 50-degree angle, but it's going to produce this much thinner tail, right? So this tail is going to point in the direction that blood kept moving. There may be secondary or satellite drops that appear in front of that moving droplet of blood. So we may see extra drops of blood over here, little extra drops over there. So if you look at that overall pattern, you can get an idea of how this moved. So we can determine quite a bit about what was going on with this blood drop based on individual drops, or based on the mathematical relationship. So let's talk a little bit about determining the angle of impact. So like I said, there is that mathematical relationship between the width and the length of the blood drop. We can plug in the measured width and length of any individual blood drop into a very simple formula. And this will allow us to determine what angle that blood drop hit a particular surface at. remember back to geometry. Now, if you were like me, you liked geometry the best of all the maths, because, you know, you've got to play with fun shapes, and I really enjoyed doing like proofs and that sort of thing. But for the most part, I kind of hated math when I was in high school and when I was in college. This was until I figured out that math can tell us all manner of amazing things. We've looked at several formula throughout this semester, throughout this class so far. This is just another one of them. So if you think about every time you're sitting in your math class or you're reading a math book, what can this tell me about the world around me? That always helped me understand why I was trying to memorize all these stupid formula. This is one formula that I want you to know. It's that geometric relationship between the width and the length of a blood drop. So if we measure the width, and you're going to measure the width of a blood drop based on its fattest point. So here we've got a blood drop. You find its like fattest area. You can draw a line, and you can measure between here, and that'll give you the width. And then you find the tip of the blood drop. Now, when you do a blood drop, you're not going to include this extra tail. So remember, this tail tells you what direction it's going. So this blood drop's hit up here and moved in this downward direction. You're not going to include that tail. Anywhere that blood drop gets really, really thick and sort of pointy like that, you're going to cut that off. So the length is going to be the main body. So you're going to measure that length. The length should always be bigger than the width in an elongate blood drop. In a circular blood drop, they should be equal. But you're going to do width at the fattest point, length at the tallest point, minus that tail. So you're going to divide the width by the length, and then you're going to take the inverse sign. So when you take the inverse sign of this particular ratio, that number that you're going to come up with is the impact angle, or the angle of impact, AOI. Okay? If you get something that's close to 90, that means that it was a perpendicular drop. It dropped just above the surface, so you get that circular blood drop. So your ratio should be very close to 1 in that case, where the width equals the length. If it was, less than 10 degrees, that means it hit at a very, very sharp angle. So doing these basic formula. So this is the geometry that I'm talking about up here. So let's say we've got our spherical blood drop. Remember that blood always drops as a sphere, even if it's going at weird angles, until it hits a surface. Then as it hits that surface, this is the geometry that we are attempting to calculate. So you have this right angle, and this right here, you can use the sine function to calculate this angle. And that's the angle we care about. This is the angle at which this blood drop hit. So think way back to your geometry. Look, it's super useful. Okay, then you got your secondary splashes, you got your length, you got your width over here, and this is the direction that the blood was traveling from. So this is what it looks like above. Secondary splashes over here, got your length, and you got your width. So this is your formula. You got your inverse sine times the width, or the sine, equals the width over the length. Sine of that angle equals the width over the length. Now, what we need to do is you need to measure the width, measure the length, and just plug it into this basic formula. So here is a quick example. Let's say I've got the a 10 millimeter width and a 20 millimeter length. I divide 10 by 20, get 0.5, take the sine of the angle, or the inverse sine, the arc sine of that, and I end up with 30. So the angle of impact is 30 degrees. So this hit that wall at a 30-degree angle. Let's walk through an example of this, shall we? If you haven't figured out how to use your phone, say, as a scientific calculator, I have a little picture of it up here. I also have a video for you up under the help section on how to use an iPhone as a scientific calculator, because I've gotten a few questions. But all you need to do is you need to open up your calculator and then turn your phone sideways, and you'll get your scientific section here. Then if you click the second, you'll get the inverse of everything that you need. Okay, now let's say I've got a blood drop. The width is 2.6 centimeters. So from the fattest point, we got 2.6 centimeters. The length is 5.9 centimeters. Whenever you're doing this calculation, you're going to want to do this in centimeters or millimeters. Okay. Then I'm going to plug this into my formula, the inverse sine, the arc sine, times the width over length. Okay, so remember your orders of operation here. You're going to do everything that is in the parentheses first. So let's say we've got our width over our length. So we'll take 2.6 divided by 5.9. That's going to equal 0.44. Now we take the inverse sign of that on the calculator up over here. You just hit second, and then you got your inverse sign right here. Second. And that gives us an angle of impact of 26.2 degrees. So this blood drop hit the wall at a 26.2 degree angle. Slightly different things. Let's try a blood drop that is perfectly round. See how that works out, shall we? Okay, so let's say we got a blood drop. It's 4.2 centimeters in width and 4.2 centimeters in length. Again, all we have to do is plug and play into our formula. We add that 4.2 over 4.2. That equals 1. Take the inverse sign of 1. You get 90. Hey, it hit at a 90-degree angle. Awesome. That's the basics of calculating the angle of impact. I'm going to have you do a lot of these calculations just so you get the idea down. Exactly what are these angles of impact? If you have any questions, just let me know. Next, we're going to be looking at blood spatter points of convergence to see how we can use these angles of impact to actually recreate what happened at the scene.